So now that we've worked through the area problem, we've got an idea of how the area is related to this integral symbol. Let's talk more about the definite integral. All right, so there's that symbol again, right? The integral from a to b of f of x dx. So again, that's how I would say that. The integral from a to b of f of x dx. All right, collectively, this is called a definite integral. And again, that elongated S symbol is the integral sign. A is the lower limit of the integration. B is the upper limit of the integration. Collectively, A and B are called the limits of integration. F of x is called the integrand. The dx is the differential. And it tells us, again, it tells us where the integral closes, right, where it ends. And it tells us that the independent variable in this case is x. But now there's nothing special about the x. The x is a dummy variable. So if I write the integral from a to b of f of x dx, and that's the same as writing the integral from a to b of f of r dr. As long as it's the same f, right? As long as it's the same function and the same limits, it doesn't matter what variable we use. The end value is the same. I could easily just write the integral from a to b of f of theta, d theta. There's nothing special about the x. It's just a variable. So now let's build some properties, or talk about some properties of the integral. So what we've said so far is that if the function lies entirely above the x-axis over the interval a to b, then the integral from a to b of f of x dx represents the area under the curve, right? And that's how we built that concept. And we said, okay, well, you build all the rectangles, you let the number of rectangles go to infinity, it becomes this area. All right. And we said that that area was between the x-axis and the function. Now, what happens if the function takes on positive and negative values over the interval? So here in this diagram, I have a function. This is the function f of x. And we see that it takes on some positive and negative values over the interval a to b. So now, this integral from a to b f of x dx, when we think of this integral, we think of it as being two regions. Here we have region, I'll call this A1. Here's A1. And then here's A2. And here's the second region. And so then if the function takes on positive and negative values, then we would think of the integral from a to b of f of x dx as being that area of region 1, so A1 minus A2. So it's a net area. And what this also means then is if the region is below the x-axis, we consider the area to be negative. All right, so that might seem a little different than how we've considered area in the past, right? We don't really think of the area as, say, a rectangle as having a negative value. But if you think about how we've built that concept, if I was to draw a rectangle, in this region and find the area using a sample point, that sample point would have a negative value. So if I took the width times the height, and the height being a negative number, it makes sense, it's reasonable to think of this area as being a negative value. Alright, so now let's talk about some more properties of the definite integral. For these properties, let's assume now that a is less than b. Alright, so if a is less than b, now what if we have the integral from b to a of f of x dx? And so far, we've been thinking of the integral from a to b, recalling that a is less than b. The integral from a to b gives us that area. Well, if instead we have the integral from b to a, then if we think about our delta x, if we were thinking of that Riemann sum, our delta x would then be, instead of b minus a, it would be a minus b over n, which is -1 times b minus a over n. And so then our delta x is the opposite of the delta x we used to build the original integral, and so it seems reasonable then that the integral from b to a of f of x dx would be the opposite of the integral from a to b of f of x dx. So if we interchange the limits of integration, we get the opposite of the integral. All right, similarly here, if we have the integral from a to a of f of x dx, then our delta x here, well, that would be a minus a over n, and so that would be 0. And so we would be multiplying, each of those terms would be times 0, and so in a sense, if we think of the area as being over a width, we've now shrunk the width down to 0, and so there's no area. And so then the integral from a to a of f of x dx is exactly 0. All right, what about the integral from a to b of k dx, where k is a constant? All right, so now this one, let's use a geometric argument here. If k is a constant, so let's think of this real quick. And so here's a, and here's b. And if k is a constant function, so here's my constant function k, then the area that we're finding through this integral is exactly that of a rectangle. And so it's a rectangle of width, b minus a, and height, k. And so then this area, all right, thinking of this integral as an area, this integral is just the constant times b minus a. All right, what if we have the integral from a to b of a constant times some function? And so now the constant times a function, that's a scalar multiplier, right? So that takes the height of the function and just multiplies it by some value k. So it should seem reasonable that if we know the original integral, if we know the original value, and we're multiplying that original function by k, it should seem reasonable that we would scale the area. And in fact, that's what happens. So the integral from a to b of k times f of x dx is k times the integral from a to b of f of x dx. Now it's very important, this k must be a constant. The k cannot be in terms of that variable x. It must be a constant. If that factor involves the x, this doesn't apply. We cannot break it up if it's not a constant. If we have the integral from a to b of a sum or difference of functions, we can break it up term-wise. That's a legal move. So this is the same as writing the integral from a to b of f of x dx plus the integral from a to b, or minus, right, depending on what we were given, a to b of g of x dx. So if we have an integral that has multiple terms, we are allowed to break up the integral into multiple terms. And finally, another important property is that if we have the integral from a to c of f of x dx plus the integral from c to b of f of x dx, and notice how it's the same function, right? Same function, same differential, same integrand, I should say, right? That's the appropriate word. Same integrand and differential. And notice that we're going from a to c, and then from c to b. And so if we have something like this, we can rewrite this as a single integral from a to b of f of x dx. So those are some basic properties of the definite integral, and we'll see a couple more as we progress, but those are some important properties we need to be aware of. And so now let's get a little bit of practice evaluating integrals, and we're going to have to use geometric arguments for now, thinking in terms of the shapes of the functions. In the next topic, we see a really important, in fact, it's so important it's called the fundamental theorem of calculus that gives us a general way that we can evaluate integrals. But for now, we're going to have to think in terms of geometric arguments. So let's see those. All right, evaluate the integral, and we have the integral from 2 to 7 of 6 dx. All right, so what I would notice is that this 6 is a constant. It is not dependent on x. It's a constant. And so if we think back to what we saw on the previous slide, then this would be equal to 6 times 7 minus 2. And so then that's 6 times 5, that's 30. And again, the geometric argument here would be that I'm integrating from 2 to 7. So here's 2 and here's 7 on the x-axis. And I have the function 6. There's the function 6. And so I'm finding this area between 2 and 7 and between the x-axis and 6. And that's a rectangle. And the area of a rectangle is just its length times its width. The width is 5. The length, height, is 6. 5 times 6 is 30. The integral from 3 to 10 of 1/2 x plus 5 dx. All right, this one's a little tougher. For now, we're going to have to use geometric arguments, and I'm also going to use some properties. So I can start this off by saying, well, if I break this out using properties, I can turn this into two terms, and I see, so then this is the integral from 3 to 10 of 1/2 x dx plus the integral from 3 to 10 of 5 dx. Now the second term here, the integral from 3 to 10 of 5 dx, that's similar to the previous exercise because 5 is a constant. But this one, 1/2 x is not a constant. But I do have the 1/2 as a constant factor. I can bring that outside the integral. So then this becomes 1/2 integral 3 to 10 of x dx plus the integral from 3 to 10 of 5 dx. Now again, that second term isn't too difficult, but now let's focus on this factor right here. What's the integral from 3 to 10 of x dx? And again, what I'll do here is use a geometric argument. So there's my axes. Here's the function x. That's just a line through the origin with a slope of 1. And I'm integrating from 3 to 10. And so then my shape, if I think geometrically, this shape is a trapezoid. It's a trapezoid, and it has heights 3 and 10, or bases 3 and 10. And the width, the height of the trapezoid is 7. And so if you remember back from geometry, the area then would be 1/2 times 3 plus 10, half the sum of the bases, times the height, which is 7. So that's 3 plus 10 is 13. 13 times 7 is 91. Half of 91, I'll just write that as 91 over 2. And so then this integral becomes 1/2 times 91 over 2. Now the second integral, in purple, right, this integral, using basically the previous exercise, that's 5 times 10 minus 3. And so then that would be 35. So then I have 1/2 times 91 over 2 plus 35. And now it's just arithmetic. 91 over 4 plus 35. And I did this earlier. This ends up being 231 over 4. Or 57.75 as a decimal number. All right, this third example, here we have the integral from 0 to 6 of the square root of 36 minus x squared dx. Now, I can't break that up, right? I can't turn that into the square root of 36 and minus the square root of x squared. It just doesn't work. That's not how radicals behave. So I have to do something different. All right, so here's what I'm going to do. I'm going to think of this temporarily as some y. So y is equal to the square root of 36 minus x squared. Now if I square both sides, then y squared is 36 minus x squared. And let's add the x squared to both sides. Then x squared plus y squared is 36. And hopefully you recognize this now as a circle with center at the origin and radius of 6. All right, so I'm going to try and draw this poorly. Right? So it might look something like this. Poorly drawn, I apologize. I'm trying to do this freehand. All right, so there's my circle of radius 6 centered at the origin. Okay, but wait a second. We were given the positive root, right? This was the positive root. And so then this is the upper half of the circle. So it's only the upper half of the circle. Now, we were integrating from 0 to 6, right? We were integrating from 0 to 6. So we want the area of this shape from 0 to 6. So we're only looking for this area. And so that area is a quarter of a circle. Well, I know how to find the area of a circle. The area of a circle is pi times the radius square. So that's a quarter of pi times 6 square. 6 square is 36. So the area of the entire circle is 36 pi. A quarter of that then is 9 pi. All right, so that integral is 9 pi. And in fact, now, actually this integral, using the method that we're going to learn in the next topic, would actually be very difficult to evaluate. However, if we use a geometric argument, it's not that difficult. We just have to understand what that function represents and then apply it correctly. All right, let's look at a couple more examples. All right, so here we're given some information about a couple of functions. We are told that the integral from -2 to 5 of f of x dx is 12, and the integral from -2 to 5 of g of x dx is -6. And then we're asked to evaluate a couple of expressions. Why don't you pause and try these out on your own before I do them? All right, so the first one here, we have the integral from 5 to -2. All right, so this one's really not too bad. Notice that that's the same limits of integration, just I've switched the order. So this is the same as the integral, as the opposite of the integral from -2 to 5 of f of x dx. So then this would be the opposite of 12, -12. Then I have the integral from -2 to 5 of -3 f of x plus 4 g of x dx. So then I can break this up. There's multiple terms, so let's break it up by term-wise. This becomes the integral from -2 to 5 of -3 f of x dx plus the integral from -2 to 5 of 4 g of x dx. Then using another property of integrals, since the negative 3 is a constant factor and the 4 is a constant factor, I'm allowed to bring those out. So then that's negative 3 integral negative 2 to 5 f of x dx plus 4 times the integral negative 2 to 5 g of x dx. And now each of those, we were given information on them. So then that's negative 3 times 12 plus 4 times negative 6, and now it's just arithmetic. Negative 36 plus negative 24 is negative 60. All right, so that concludes this video. And we're going to, like I mentioned before, we're going to learn another technique for evaluating definite integrals. And it's a really important idea, and you'll use that from now on in any class, any concept that really requires calculus, I should say integral calculus. But we'll see that in the next section. It's called the Fundamental Theorem of Calculus. All right, have a good one.